Hello, this is Mr. Vanskoy again. In this video, we're going to be it's our unit on plate tectonics. We're actually going to be talking about the theory of plate tectonics. So when you're done with this lesson, you should be able to explain the theory of plate tectonics. We've already talked a little bit about the brief history with continental drift. And so in this one, we're going to focus on current evidence that adds to that, and really then kind of that transition from continental drift to the theory of plate tectonics. So one of the things that sets apart, one of the big things that sets apart the theory of plate tectonics from continental drift is that in plate tectonics, scientists are offering an explanation as to what is causing those plate motions. And to date, our best evidence points to a couple of different things. The main one being convection currents in the mantle. So as in this example here, we kind of have what's called a slab pull. As this convection current is coming up, there's going to be a frictional force between that convection current and the crust that's up above it. So it's going to kind of drag that along as it moves in its cycle. And then kind of same thing over here on this side, but in the other direction. So oceanic crust and continental crust would be kind of drug along by those convection cells in the mantle. And also, which kind of supports and adds to this same idea, is that the dense oceanic crust is going to be pulled down just due to gravity. So in places where you have oceanic crust, that crust is going to be a lot denser than the continental crust. So anywhere that that's happening, that denser crust will be pulled down or assisted because of the gravitational force pulling it down. So some of the other evidence then that kind of led up to plate tectonics, kind of a crazy idea to think about at first, but the planet itself is ripping apart, and there is a 12,000 mile long mountain range in our ocean. Okay, it's always been there, or at least in recent millennia, but we've only recently discovered it really in the last 50 years or so, because it is covered anywhere from a mile, 2 miles worth of ocean water. So only when actually the military and then later scientists started mapping the ocean floor did we discover this, literally make this huge discovery of the mid-ocean ridge. And besides the fact that it's this massive ocean ridge kind of encircling the globe, Henry Hess discovered that the seafloor was actually spreading at this mid-ocean ridge. So we have that's the ripping apart part of my earlier statement, that the ocean floor is ripping apart and it's actually being pushed up as it's being ripped apart from underneath. So as it's kind of pulling apart in these different directions, there's an upward force. There's an upward force of that magma as it rises up, and so it is going to be some uplift to that. Very quick diagram, very bad diagram, but I think you get the idea. So there's that upwelling there from the magma. So this in and of itself was pretty amazing, but what then further adds to this idea, kind of the cool factor, is our next slide. So not only are there places on our ocean floor where it's being ripped apart, but something they found out was that the age of that rock, kind of lending support here to that idea that this has been going on a while, the age of that rock gets older and older as you move farther out from that mid-ocean ridge. So if here is my fancy diagram of science, mid-ocean ridge, we can have rock right in the middle here that's literally just now being formed, brand new rock, and moving our way out to either side, have rock that's 1 million, 2 million, 3 million, 4 million years old, and so on. So we have tools now where we can actually measure the age of that rock, and we find it in symmetry or near symmetry, where these ages have kind of matching partners on both sides of that ridge. So again, adding further evidence that our planet has got a lot going on. It is, and quite often kind of has that nickname of the dynamic planet, because we don't see all of these things happening on other planets. Again, adding evidence to plate tectonics is the earthquake, mountain range, and volcano patterns that we see along plate boundaries. And using, more precise modern mapping techniques, we start to see these quote-unquote coincidences where all of these earthquakes involve, or I shouldn't say all, but most, something in the magnitude of 90-95% of our earthquakes and volcanoes are going to occur in just these locations, and those locations we are now finding out are plate boundaries. Same things with mountain locations. They start to show patterns there too as to where they're being formed. And literally, we can measure the plate movement, very precisely now. We can, in previous years, we kind of suspected and we could infer how fast some of these plates are moving. But with modern instruments and tools, we can actually measure the Earth as it moves in different locations. And it does depend on the plate that you're measuring, but on average, we're talking about a few centimeters per year. So it doesn't seem like a whole lot, and we're literally talking about, or the analogy of your fingernail growth. You don't notice that from day to day, but a week goes by, maybe 2 or 3, and then you start to notice that, hey, my nails are getting long. But on a day-to-day basis, you don't notice that your fingernails are growing. So kind of the same idea with the plate motions. And so I've been talking about plates. What we're talking about here are lithospheric plates. And that crust that we live on, that hard crust, is broken up into these pieces that are called plates, or lithospheric plates, that slowly move in a variety of different directions. They're not all moving in the same direction. And I'm not sure how well you can see this, but you can see here on this plate, it's moving in this direction, and our North American plate is moving in that direction, kind of a southeasterly direction. And right along that edge we call those plate boundaries, not surprisingly, we find lots of earthquakes and volcanoes. And where we find earthquakes and volcanoes does depend on the type of plate motion. At convergent boundaries, we're going to find things like mountains and volcanoes. At divergent boundaries, we're going to find different kinds of volcanoes and actually not as many earthquakes. At transform boundaries, we're going to find more of those earthquakes. So again, just kind of to reiterate, our lithospheric plates are always in motion. And I'd mentioned some terms here just a moment ago. And again, I'm going to kind of blow through these quite quickly. I'm hoping that these are mostly review terms. So when we have plates colliding and they're coming together, we call those convergent boundaries. So anytime we have plates that are coming together, they're convergent boundaries. Con meaning with, and verge meaning to turn, so kind of literally meaning turning with boundaries. Plates that are separating or going apart are divergent boundaries. And again, kind of some vocab builder here. verge meaning to turn, and di meaning two. So we're actually talking about turning in two different directions here, divergent boundaries. And then our last one, we have our plates sliding past each other, generally in opposite directions here. So sliding past each other in this direction, in that direction there. Those are going to be transform boundaries. So kind of across from each other, moving in different directions. And of course, they don't have to be oriented that way. They could be oriented, lined up this direction here too. So, and like everything, when we're trying to classify things in nature and science, there's kind of in between boundaries as well, right? So we kind of have these three basic ones, but we can actually have different types of combinations or mashups of those three. So generally speaking, as we talked about, as I mentioned already, earthquakes, volcanoes, and mountain buildings, and also just the shape of our planet in general are always shifting. These are all results of plate tectonics. All right, so hopefully that helps you understand the theory of plate tectonics a little better. And as always, if you have questions, ask.